Welcome to This Explainer. Today, we're going to do something really cool. We are going to demystify the invisible infrastructure of our digital health systems. You know, we rely on these healthcare networks to be fast, reliable, and perfectly accurate. But have you ever actually stopped to wonder how exactly all these medical devices communicate with each other? Well, we're going to decode the secret language of hospital networks and figure out exactly how data travels from point A to point B. To really appreciate how this works, I want you to picture a massive, bustling modern hospital. Just imagine it, 500 computers scattered across all these different wards, 50 printers down various hallways, 20 servers humming away down in a basement somewhere, and 100 doctors walking around with tablets. Now, a doctor in the emergency room needs a patient's medical record right this second, and they click a button on their screen. How in the world does their specific computer know exactly where to find that single piece of information amidst hundreds of other connected devices? It's honestly a massive routing mystery. Without a strictly organized system, this entire network would be absolute chaos. Imagine trying to find one specific file in a giant library where literally none of the books have titles or shelf numbers. It'd be impossible, right? So the network needs a way to bring order to the chaos, ensuring that life-saving data reaches the right doctor at the exact right time without just getting lost in the digital void. Section 1. IP addresses. Like a house address. Okay, let's dive into this by looking at our very first core concept. It all starts with the IP address, which stands for Internet Protocol. To kind of de-jargonize this a bit for us, an IP address is simply a logical, numerical identifier that gets assigned to a device on a network. Its entire job is to identify and locate devices. That's the whole shebang. It's absolutely fundamental. Without IP addresses, websites wouldn't load, your emails wouldn't send, electronic medical records would be completely inaccessible, and hospital networks would simply break down entirely. The analogy here is wonderfully simple. Think of an IP address exactly like a house address. Imagine every house in a city, house 12, house 25, house 78. If your house didn't have an address, the postman wouldn't have a clue where to deliver your letters. Computers operate on the exact same logic. Every computer, printer, and server needs an address so other computers can find it to deliver data. So if a physical room in the hospital is room 101, its digital equivalent might be an IP like 192.168.1.10. But, not all addresses are exactly the same. We have to draw a distinct line between private IP addresses and public IP addresses. Private IPs are used exclusively inside organizations. For instance, a doctor's workstation tucked away safely inside the hospital network might have an address like 192.168.1.100. You cannot reach that computer directly from the outside internet. Public IP addresses, on the other hand, are outward-facing. They sit on the global internet, using formats like 196.x.x.x. Think of the public IP as the main street address of the entire hospital building, while those private IPs are the internal room numbers that only the hospital's internal router knows how to navigate. Section 2. IPv4 versus IPv6. Future-proofing. Let's look at how the internet is adapting to a massive logistical problem. So, for a long time, we relied entirely on IPv4. These are structured in 4 sections, called octets, separated by periods, something like 192.168.1.10. Now, because each octet only ranges from 0 to 255, there's a strict mathematical limit to how many unique addresses we can create. And honestly, we're running out of space worldwide. The solution to this is IPv6. IPv6 uses a much longer, far more complex string of characters. This newer format provides a near infinite number of available addresses, offering incredible scalability for the rapidly growing number of connected medical devices. It's essentially future-proofing the internet. Section 3. MAC addresses, a digital fingerprint. Moving to the next layer of our analogy stack. All right, this brings us to the MAC address, or Media Access Control Address. And it's absolutely crucial to firmly distinguish this from an IP address. An IP address is a logical address that can change. If you take your laptop from your home to a local coffee shop, your IP address changes, just like moving to a new house means you get a new house address. A MAC address, however, is a physical address burned right into the device's network card. It's permanent. It identifies exactly what the physical device is on the local network. And this brilliantly illustrates the whole concept. It really comes down to this. If the IP address is where you live, the MAC address is who you are. It's your permanent digital fingerprint. Even if you move to a new house and get a new IP address, your fingerprint never changes. every single tablet, server, and Wi-Fi-enabled heart monitor in a hospital has its own permanent MAC address fingerprint. Section 4. Domain Name System, the Internet Phone Book. Let's pivot to the human element of networking. So, numbers and fingerprints are great for computers, but let's be real, they're terrible for humans. We prefer names. We want to type muhas.ac.tz or google.com, not some clunky string of numbers. Computers, however, only speak numbers. They have to have an IP address to connect. This is where DNS, or the Domain Name System, steps in. DNS acts exactly like a phone book. You know the name of the hospital server you want to reach, and DNS looks up the numerical IP address so your computer can dial. Let's just pause on this thought for a second. Without DNS, the internet would be almost completely unusable for us. Because we literally rely on this invisible translation service every single time we open a browser. Here is exactly how this fraction of a second process works. Step 1. The user types a human-readable URL or domain name into their browser. Step 2. That request is sent to a DNS server, which rapidly scans its records. Step 3. The DNS server finds the match and returns the real numerical IP address. Step 4. Armed with the correct IP, the user's browser securely connects to the target, and bam, the website opens. When a doctor types a link to open the EMR, the domain name system instantly converts that text into a routing IP, like 172.16.10.5. Section 5. Device Communication. How it happens. Time to bring it all together. Okay, let's bring this entire analogy-driven journey together to solve the routing mystery we introduced right at the start. Let's see how all of this builds our final picture of network communication. We have the doctor on their PC, uniquely identified on the hospital's private network as 192.168.1.10. They need patient data. They type in the hostname for the electronic medical records server. DNS works its magic in the background, identifying the target server's IP address as 192.168.1.100. The doctor's PC wraps up a digital request and stamps the destination IP address right on it. The hospital network acts like the post office, looking at the IP address, checking the permanent MAC addresses locally, and sending the message through the wires straight to the EMR server. The server processes the request, stamps the doctor's IP address on the returning data, and sends the patient file right back. Communication completed perfectly. So, what does this all mean? The crucial point is this. We've just mapped out how every device finds every other device. But this transparency, it's kind of a double-edged sword. Security scanning and exploitation tools like Nmap, Wireshark, OpenVAS, and Metasploit, they all rely heavily on this exact same understanding of IP and MAC addresses. If a basic understanding of how these addresses work is all it takes to map an entire hospital's digital infrastructure, room by room, how secure the network you rely on today? That foundational question is exactly why understanding these core concepts is the necessary first step before we can even begin to talk about scanning and securing our digital health systems.